Okay, so this class 1 we're going to be wrapping up the remaining little bits of circular functions, finishing up with applications of circular functions. So in the context of Unit 1 and 2, you're pretty much going to be given two different kinds of questions where they're more or less just sort of subsets of each other. And what I mean by that is the first kind of question, you'll be given a circular function of some sort and you'll be told to analyze parts of it, right? Like if we have a quick squiz at what's going on here, h of t is a height of tide levels, right? And we're given the full function. We're doing things like drawing the graph, identifying when there's a high tide, what is the height of the high tide, heights at different time levels, all of this sort of stuff, other kinds of analysis. In fact, one of the toughest ones is going to be part E, which is it's going to give more context around the scenario and try to figure out like different time durations rather than specific time values. So we'll ask these kinds of questions. The other kind of question type pretty much just takes a step back from this and makes you solve the entire function itself. Right, so you don't get given the function. What you get given is a generic version of that function and a bunch of information that can help you create that function. And then they ask the follow-up questions on top of that. So let's just start by going into a bit more detail with the analysis of when we do have the function. So first up, drawing the graph. We all know how to draw circular function graphs at this point now. Just because there is an application behind it doesn't mean the rules of sketching that graph have changed in any way. It's a circular function that is a sine graph, so it's going to start at the origin. It's going to peak and trough at plus minus 4, because that's our amplitude. It's going to have a period of 12 in this case, because it's 2 pi divided by pi over 6. So you get one cycle within 12, the second cycle for 24, because we wanted to sketch from 0 to 24. Now, to answer follow-up questions, when was a high tide? Considering that the y-axis, h of t, is in terms of meters, the tide above mean sea level, it means our high tide is going to be referring to the peaks of this circular function, which is why the answer is going to be 4 in that case, 4 meters above mean height. The troughs will therefore be minus 4. As for when the high tides were, depending on how you sketched it out yourself, whether you use CAS or otherwise, you may or may not have those additional key features. If you did it tech-free, you would have it already. All these individual peaks, troughs, mid-levels will always occur at quarter intervals of the period. So if the period is 12, then halving it down to 6, halving it down to 3, basically means that every single peak, middle, trough is all separated by a distance of 3. Which is why we're going to get t equals 3 for this one, and t equals 15 for this one. Both of those written there. Which you can even convert down to the time itself, depending on... usually it's best practice to give it in terms of like AM, PM, if you can. As for how you would do that, it would depend on the definition of t, right? If t is the number of hours after midnight, then you know that t equals 0 would be exactly midnight, and anything after that can be then converted to an actual AM or PM time value. Next one up, what was the height of the tide at 8 AM? Again, if necessary, you need to convert that AM or PM time into 24-hour time, because that's how t is defined. In this case, 8 AM is just going to correspond to t equals 8 anyway. So you shove in t equals 8, and you get whatever the height is out of that, which in this case, the mathematics behind that is presented there. This will be the hardest question of the lot. So we're told that a boat can only cross the harbour when the tide is at least 1 metre above mean sea level. When could the boat cross the harbour? They're given a date here. That was part of this background here. So that's a little bit irrelevant. So if we know the boat can only cross when it's at least 1 metre above sea level, we want to know, we basically have this horizontal line at y equals 1, and anything above that is valid, we can cross at that time. Anything below that is invalid, we cannot cross at that time. So the way you would go about it is starting by finding your breakpoints. And what I mean by that is if you set your y level equal to 1, your height equal to 1, and you solve the times that give you exactly 1, then all you got to do is dot out where those are on your graph. That's going to correspond to these t values, and you could draw little dots along that. And from there you can see basically anywhere between let's say these two, right? 0.4 and 5.5 is going to be like here and here. You guys can definitely see my cursor. Yeah, let me know if you can't. And so yeah, anything between those is going to be valid, and anything between 12.4 and 17.5 is going to be valid. Anything underneath or anything outside of that will be invalid, which is what they've said here. They're using 24-hour time. You can use AM, PM. It's up to you. That's pretty much it there. Were there any questions about interpreting any of that? Cool. That's the main part that you'll get, which will be interpretation, and pretty much will always be in your circular function applications. What may also be in there will be actually finding the function itself. So basically put, you'll get a lot of background information, and it's your goal to create the equation that describes everything in there. These are more so guidelines than individual steps you have to follow in that particular order. The only thing that actually has an order is making sure you do any horizontal translation terms last. This is because circular functions are a bit unique in the sense that different horizontal translation terms can actually achieve the exact same thing. That's because it's periodic, right? If you choose your horizontal translation of 2, for instance, and the period is 12, then if you chose 14, it would be effectively the same translation because you're doing one period shifted later. So all that to say, basically, because there's so much variance on how this one works, it's best to solve all the other key terms in your function and then back solve for this at the end. So let's have a look at an example. Again, another tide example. The time between high tides is 12 hours, average depth of water is 5, high tide depth is 8. This is our function. T is once again number of hours after noon. Well, I guess in this case it's just after noon, not after midnight. And finally, at noon, there is a high tide. So again, you can do a lot of things in different orders here. This is just one possible way of going about it, mainly just trying to hit all the key things in the question. So first up, we're going to try and identify what the period is in this scenario, and that is going to allow us to solve for n, because the period is calculated by 2 pi divided by n. That's going to be this first piece of information here. The time between high tides is 12 hours. That is by definition the period, because the period is simply just how long it takes for your circular function to repeat once. So if you think about tidal waves going between high tides and low tides, you don't necessarily want to find the time between high and low. You want to find time between high, low, and then high, which is what this is, right? Time between individual high tides together. That's why that's going to be a period of 12 rather than like a period of 6, for instance. Since the period is 12, we can now equate that to 2 pi divided by n, and sure enough, we can now quickly solve for n. Okay, that gets us our n term, which is depicted there. From here, next up, we can have a look at the vertical translation. So the vertical translation in the question is given by the variable b. The vertical translation is always going to be the mid-level of the circular function, or the average of the circular function, or at least in the case of our scenario, because our y values are heights, it's going to be the middle height that's given to us. So if we're told the average depth of water is 5, that means that when you consider your high, when you consider your low, the average, the middle, is going to be 5. Which is why our vertical translation, in this case given by b, is just going to be 5. Any questions there so far? Next up, let's have a look at the amplitude. So sometimes this will be given to you immediately in the question information itself. If it's not, you have a few ways of calculating depending on what information you have. If you have the peak and the mid-level, like we do here, right, we have the high tide, which is a peak, and we have the middle, the average, then you can just find the difference of those two things, and that's going to be your amplitude, which is what we're doing exactly here. Peak of 8, middle of 5, that's going to give us an amplitude of 3. Alternatively, if you had the trough and the middle, or the peak and the trough, there's a bunch of different ways you can now go about it from there. Just using the information that you have to work your way back to the average. One slight quote problem here is that depending on how you calculate this, you might get a positive or a negative number. And in a lot of different wordings, in a lot of wordings of these questions, both options are valid. Specifically, if you have a horizontal translation available to you in the question will be worded in such a way where you could actually have both positive or negative for your amplitude here. So unless they are at the start of the question telling you what it has to be, or there's some further information that would make it super clear that it has to be positive, you kind of have a lot of freedom here. So we're just going to pick positive because positives are usually easier to work with. Lastly, if we recap everything we've done our amplitude, we've done the end term from the period, we've done our vertical translation, all that's left is the horizontal translation. So if all that's left is the horizontal translation, if there were some way to remove the t and the h, replacing those with actual known values, then that would be the only variable left in the equation. And because it's the only variable left in the equation, we should be able to solve for it. So if we have a scroll through all the information that we have, we've already used this one, we've already used this one, we've already used this one. This isn't really information, it's just describing the function. This is describing, again, the definition of t. But then there's this last statement here. At noon, there is a high tide. That is a known point on the graph. At noon, time value, there is a high tide, height value, time height. That's going to be a t value and a h value. We know a high tide is 8, and we know noon is going to be t equals 0, because t is the number of hours after noon. So exactly noon would be t equals 0. So we do exactly that. Shove in t equals 0, height equals 8, and continue to solve or simplify all the way down to a solvable circular function. This is where you can see that getting multiple solutions is valid, because you get down to just solving where does sine equal 1. Yes, it equals 1 at pi on 2, but it could also be at 5 pi on 2 if you continue around the other evolutions. It could also go negative if you really wanted to. So you have a bunch of different options you can choose. Just pick the easiest. There's no right or wrong reason. In fact, what they'll often do in the wording for like a VCAR question, they'll say solve for the smallest positive or smallest negative possible value of epsilon or a or whatever it is. That way there's a bit more constraint around which one you actually use as your final answer. Furthermore, if you had even more interesting things that you had to do to it, like let's say a follow-up question would be to convert it to an equivalent cosine. This is where you start using your trig identities. Is that what I call them? Symmetry properties, something like that. For instance, any circular function sine and cos can be converted between each other by adding or subtracting some amount of pi over 2 to it. They'll have different versions of it depending on if you start it with sine or cos. In this case, this one's the one that we're going to be using, and that's effectively what we have here, right? It's sine of something plus pi on 2. We can therefore convert that to just cos, knocking off the pi on 2. This is only if you have to do it as a follow-up question. Both of these are perfectly valid final answers. That's about it. Any questions as to how any of that was working? Cool. We're all experts now. Awesome. Alright, let's see it then. So we'll practice a few of these, and then we'll move on to extend the chapter review if we can. So, question 1. Circular function is given to us, so this is all going to be about the analysis of what we have. First up is draw the graph. It's all assumed that we have CAS, so I'm going to go ahead and do that. So while I'm excuse me, while I'm drawing the graph, have a think about part B and how we might solve that. When was a high tide? Alright, there's our graph. How might we figure out when there was a high tide? Or I guess when was high tide? Plural rather than singular. So if we have a look at the definition... Oh, yeah, go ahead, Nihal.
We look at the period.
Yeah.
So the high tides are a period away from each other, so
Yeah, each would be a
yeah.
period separated from each other, yeah? Peak to peak, trough to trough, yep.
Yep. You're doing 1B, right?
Yeah, 1B, correct. When was high tide?
Yeah, okay. So we figure out the we figure out the period first, so
Yep, sure.
we have 2 pi over n.
Mm-hmm. So 2 pi on 6.
Yeah, so 2 pi on 6, that's going to be 12.
Yep, sure is.
Yeah, and we can divide the period by 4 to get the position of the first high tide.
Yep.
As a design function.
Yep.
So that's going to be 3. Yeah.
Yep. It's got to be 3.
Okay.
Nice.
High tide at 3, and the next high tide is 12 plus 3, which is 15.
Sure is. That's it.
Yeah.
Yeah, those are going to be our T values. So in terms of hours after midnight, if you need to then convert that to AM, PM, that's, yeah, whatever. You could even just use 24-hour time, be much nicer than that. Yeah, that's a nice little tech-free way of doing it, which is a really good skill to have, right? Knowing that each of the key features will always occur at quarter periods of each other. So finding out what your quarter period is and then going from there, really good idea. Alternatively, if we're assuming tech active, then yeah, we kind of have a whole bunch of different CAS ways of going about it. We can use the graphing tool and see if that gives us a whole number, which in this case it would, but in the case that maybe it doesn't, let's say we get some sort of decimal, then all we would do is solve for when the high tide is. If we know our high tide is y equals 5, because that's our amplitude, then you just solve for h of t equals 5. And then give all those time values, so long as you restrict your domain from 0 to 24. But yeah, nice. That gives away part C, which was what was the height of the high tide. It was going to be 5. Making sure we give a unit, I guess. So in this case, meters. H of t is in terms of meters. What was the height of the tide at 2 AM and 2 PM? Those are more or less the same question. What are we doing there? There's a D and E.
We're showing 2. So as these like the numbers after midnight, so
Mm-hmm.
2.
H2, that's going to give us a value. What about the other one? 2 p.m.
2 p.m. That's just 1400 hours, so be 714.
Yeah, exactly. And you can use the look at the graph to also circumvent even needing to sub it in at all, but good to know or revise how to convert between AM and PM. Just adding 12. Cool. Hard. Yeah, question?
Are it supposed to be degrees for this? Or radians?
Good question. Yeah, because there's pi involved in the actual function, you assume default radians here. That doesn't necessarily hold again if you look at like question 2 where there's no pi involved. Yeah, that's a good question. So these questions are practically always radians unless they literally use the degree symbol. I think I can find one where they've used, yeah, here we go. So if you have a look at question 7 here, for instance, they've literally put degrees in the actual function definition itself as a reminder. So yeah, the answer to your question is default radians assumption, unless they literally tell you degrees is what they're supposed to be using.
Yeah, but when I solve for a of x equals 14, it comes in as false. Why does that?
Oh, so you're not setting it equal to 14, you're shoving 14 as in an x value, not as a y value.
Okay.
Yeah, because if you look at our graph, we only go to plus minus 5, so it's saying
Okay.
false.
Yeah, t equals.
Yeah. Yeah, using a t value as opposed to a y value. And yeah, again, as I was going to say, false is because there is no y value that would give you 14. Or yeah, there is no t that would give you a y equals 14. Cool. Okay. Next up, part F. We saw this question a little bit already. We're just going to now see how much we remember from it. A boat can only cross when the tide is at least 2.5 meters above mean sea level. When could the boat cross the harbour on this day? Final question of part 1.
So this one's an inequality question, so we can set up the equation to be yeah, so f of x is greater than 2.5.
Greater than 2.5, comma x. I'll just put a domain on it. 0 less than equal to x less than equal to 24. Okay, so we get that. That's a bit interesting. 2.5 meters above. I guess technically this should be an inclusive because at least 2.5 would include it, but I don't think that's going to change our answer, what we get. Maybe it will, I don't know. Yeah, it makes it worse actually. Awesome. Okay, so the CAS is kind of failing us a little bit here.
For me, it gives 4 extra.
It gives you 4 answers.
Yeah.
Yeah, sick. I wonder why mine's just shit in the bed for some reason. Because it should give 4 answers.
I guess we can work around this, so
Yeah.
we can just set it equal to 2.5
That's right.
and then
Oh,
check
is
the
it? Yeah,
graph
okay.
and see like where it's like above, like what and within what interval is it above 2.5.
Yeah, so like a nice little visual of that. If I get back to the function, there we go. If I set that equal to the, giving us our little height there, then you got the, oh, I remember the t equals 1. There was that. I think it was t equals 5 next, something like that. So between 1 and 5, and then I guess that would make it 13 and 17. Did I get those good? Yeah, I did. So you find your 2 boundaries, and because you want to be above that, then you go above. Yeah. So yeah, doing the actual inequality gives you a little bit of bad behavior. It's a correct answer because, yeah, I don't really know why. Maybe if I did 0 to 12, it would give, let's have a look. No, what if I did 0 to 6? Because now that should only have two solutions. Oh, one solution. Still no. Yeah, okay. So CAS inequalities with circular functions just tend not to be too super legible. So best bet is, again, as we discussed here, finding a breakpoint and then looking, do I want, excuse me, do I want to be above or below that line? Awesome. Let's find a question where we've got to create our own equation. Does such a thing exist? Yes. Okay. Excuse me. Let's have a look at 8 here. For each of the following, construct a formula involving a circular function, which could be used to model the situation. Part A. Water depths in a canal vary between a minimum of 3, maximum of 6 over a 24-hour period. There's a... Yeah, okay, why not? They're a little bit simplistic, but we'll go for it. Oh, it's actually not too bad. It's got a bit of depth to it. Okay, so we're given pretty much no real guidance here as to what circular function to even use. Could use sine or cos. Definitely don't want to use tan though. Min of 3 meters, max of 6, 24-hour period. There's a couple ways you could interpret that actually. Because the last couple of times we saw wave, tidal wave things, we had 2 periods fitting within 24 hours. So realistically that should kind of say the period is 12 hours. So long as you have your peaks and troughs within that. Let's turn up this brightness. Okay, now let's just get all the key stuff down, because this is all going to relate to different key terms of our circular function. So we have a peak of 6, maximum of 6 meters. We have a trough of 3, because that's the minimum. And the period, well, I guess I kind of used T already. Maybe go max and min instead. Max of 6, min of 3, period of 12. And again, we're choosing 12 just because the other questions would have 2 cycles within a 24-hour period. It's probably just as fine to choose one. Choose 24 instead. Alright, how are we going to tackle it from here? One of the challenges will be whether you choose sine or cos. In this case, it's not actually going to matter. We don't really have any time-related information that corresponds with these peaks or troughs. So unless you actually have time information that goes with your height information, or x information that goes along with your y information, you can actually choose either, because sine and cos have the same overall shape. So let's just, for simplicity's sake, say that we're starting with sine. We need to know the a that we're going to have. We need to know the n. We might need to know a horizontal translation if it exists. H. And we might need a vertical translation if it exists. There's one thing here that's quite quickly calculatable, regardless of whether you use sine or cos. It's going to be the n term. because it's consistent across both. How can we get n from the information that we have?
Since the period is 12, you put it on the 2 pi.
Yep, that's it. So 12 is therefore equal to 2 pi on n, and just like you said, it'll end up being under 2 pi because you multiply the n to the other side and divide by 12. 2 pi divided by 12, pi on 6. We are now a third of the way there. It's completing our circular function. Nice. We get a max of 6 and a min of 3. That tells us, well, we'll need to do a calculation with it before we can use that information exactly. Max and mins are related to the peaks and troughs of the circular function. What of the terms that we have left influence peaks and troughs of a circular function? We got A, we got H, we got C. Which of those influence where your peaks and troughs are going to occur on a y value?
A.
Yep, A. That's going to have an influence. How can we calculate what the influence was? So like maybe even before we get some hard numbers.
Difference.
Oh yeah, go ahead, sorry.
Get the difference and then divide it by 2.
Yeah, difference divided by 2. That will be, yeah, because what you're seeing is the absolute jump between the two, and then by dividing it by 2 you're getting the half jump, which by definition is our amplitude. So we got 6 take 3, which gets us to, of course, 3, and then halving that to 1.5, or you can use 3 on 2. Either way. That's it. Got our A value. Only one left is the C. C being the vertical translation. Again, related to those max and mins. So if we get a rough picture of what's going on so far, just to give a visual, we've got 6 here, we've got 3 here, and we know our circular function, I guess it's sine, so it's got to start in the middle. At least we're choosing sine. And then it's doing this and that up until t equals 24. Have I done that properly? 1. No, I went too far. Cuts off here. That's what we got going on so far. That allowed us to calculate our amplitude. We got our n in there as well. Vertical translation. What does that tell us about the circular function? Vertical translation tells us the mid-level, so the midline, right? It's the middle in between the peak and the trough. So in other words, we just need to find the midpoint of 6 and 3. A couple ways you can do it. You can use the midpoint calculation, which is just adding the two together and dividing by 2. Alternatively, you already know the half distance between them, right? The half distance is already 1.5. So if you just add 1.5 to 3, you'll also get to the 4.5 answer that you want. So in total, when it comes to writing out the full circular function here, we're going to have 3 on 2, or 1.5 for our amplitude. Sine or cos is kind of irrelevant, at least for this one. Pi on 6 is our n, no horizontal translation, and plus 4.5, because our midline is at 4.5. The reason why there's no horizontal translation is because I could draw this exact same graph with any offset that I wanted and still maintain a max of 6, a min of 3, and the period of 12. Doesn't matter what horizontal offset I do. So there's not enough information to force you one way or the other, and so you might as well just elect to not have a horizontal translation. Same thing with sine or cos, right? I could have made this start at a peak and continue on doing its thing. You're still oscillating between still oscillating between 6 and 3 and having the exact same period within 24 hours. Any clarifications there? Cool. Okay. Part B is the exact same thing, but this time doing like hours of daylight. So this is one of the weird ones where you're getting time on both the y and the x-axis, where you've got hours of daylight on the y-axis, that's time, and you've got days of the year on the x-axis, which is also a time measurement. So it's one of those things where you can actually have the same, what would you call that, a fundamental unit? Physics unit? The same physical quantity on both axes, so long as they're given different distinction. But otherwise it's the same question, right? Between 2 and 22 is the same thing as saying varying between 3 and 6. Right? It's still just the things on your y-axis, and it's still a period-related information. Yeah, cool. Were there any other questions from this set that were speaking out to anyone? I think most of these are basically the same. And we can have a look at the chapter review if there's nothing else in here that anyone's keen on having a look at. But I'll just give you guys a moment or two to have a read through and see if there's anything in there that looks like it'd be too crazy to do yourself. In fact, maybe I'll get a screen grab of it. I'll get a screen grab of the remaining questions. So if you guys want to browse that and interrupt me later to go back and do one of these, then we can certainly try that. Alright. What's a good place to start? We have the function, find d on different time values. Nah. Okay, let's do question 2 maybe. Temperature inside the house is given by that temperature equation, A of T. Temperature B outside the house is given by the exact same sort of idea. Okay, so A is inside the house, B is outside the house, sure. So when it comes to finding the temperature inside the house at 8 AM, it just means we're going to be using the inside equation, not the outside equation. This is a time 8 AM. I'm not going to say much more than that, other than we're using this equation. What are we actually doing to solve 2a here? And I'll say pay close attention to the function definition. How do I find the temperature of the inside of the house at 8 AM?
Shove 4 in the equation.
Yeah, why 4?
Because it starts at 4 AM.
That's it. Yeah, T is defined as hours after 4 AM. So 8 AM is 4 hours after 8 AM. Therefore, T would be 4 by this definition. Nice. So always pays to have a look at what T is defined as and what the Y value is defined as, because it's not guaranteed to necessarily start at a 0, which in this case it's not. So that's why we're going to shove in T equals 4 instead, which is going to give us a temperature of 19.5, which is degrees. Yes, degrees. Awesome. Part B is just a freebie. Write down an expression which is D equals A minus B, and it's already telling you what's the difference between the inside and the outside temperatures. So again, writing this out is pretty whatever. So if I define The second function b, we're going to have 22 minus 5 cos pi t on 12 again, pi x on 12, and then final function d is going to be, so it's a take b, yes, a take b. If you're doing this tech free, of course, you have to now figure out how those two things combine. Shouldn't be too hard though. They both have the exact same cosine term in there, so it's like saying I have -3 cosine on one, -5 cosine on the other. When I subtract the two, I should get the difference of +2 cosine left over. And the 21 and the 22, again, are going to combine down to, in this case, -1. So it's just like treating cos, the whole cos bracket, as its own like variable x. Okay, next up, sketch that graph. Again, these are CAS enabled, so that's pretty quick. D, is there a domain? Yes, there is, 0, 24. So let's go ahead and do that. I'll actually put it in here. 0 less than equal to x less than equal to 24. And we'll set our window settings. So let's go -125. It's a bit of a chunky calculation it's trying to do. I'm surprised it took so long to graph that. Anyway, that's nice and easy. Part C is all done. Part D is the fun question. Determine when the inside temperature is less than the outside temperature. There's a couple of ways you can do it. One uses the information we just created. The other, you can go about it a different way. Another way of thinking about it would be to say, to determine when the inside temperature is a smaller number than the outside temperature. That might seem like a stupid little distinction to make, but rephrasing it that way might help you use previous information.
Would
Do
this
you graph both equations?
Yeah, you can graph both equations and then determine, you know, when's one above the other or when's one below the other. That's one way to do it, redefining from there. I think someone else had an idea as well.
will this be if when the graph is negative?
Yes, and that's the most sophisticated way to do this one here, when this graph is negative, because this is A take B, inside minus outside. So if inside is a smaller number than the outside, then that's going to be a negative result. And so looking at the combined graph and looking at when it's negative will be the fastest way to do it because you've already got the information in front of you. But exactly as was said before, right? You can absolutely just graph the first function, graph the second function, and look at when when the A graph, the inside temperature, is physically below. And we can actually just do that just for fun, just so you can see those overlapped, although I don't know how clear it's going to look. Oh wow, it's going to be really high up actually. Yeah, because we're, hang on, we got like a midline of 21, midline of 22. Yeah, okay. Actually, that'll probably help out with legibility, honestly, having them all the way up in the sky. Cool. Let's have a look. What's that going to mean? Let's go with a y-max of 30. Yep, sweet. Okay. So, A was the inside temperature, and B was the outside temperature. So if we look at this first little duration of the graph, we can see the inside, pink, is above the outside, green. Inside is higher temperature than the outside, which is why we have positive on the black. Then there's a big crossover, which is why we have negative on the black, and then finally it crosses over once more, which is why once again it goes to being positive on the black. You know, both ways of doing this are perfectly valid. There's no there's no necessarily wrong way to do this here. That's what I would have done when I did my exams, so there's no there's no shame in not doing this immediately, but it's good to know both ways. Cool. Now let's say, so what does this question actually want us to do? So determine when the inside is less than the outside, so that will be a full time duration. Yeah, sure, why not? I just got a pop up. Someone wanted to use this. I don't know if this is anyone else can see this. Anyway, whatever. So this is a full duration. We're not looking for just the breakpoints. So depending on what method you might do, you might want to find the intersection points here, which would just be menu 6 and then 4 for the intersection, or obviously go back to your calculator tool and just make the two functions equal each other. One of those is going to give you the exact value, and the other may give you an exact value. You can do it that way, as it eventually loads, or just crashes entirely. Cool, yeah, let's not do that then. Okay. Function equals other function. Zero less than equal to x less than equal to 24. That's going to give you the same thing as if I had just said find where d is exactly 0. Okay, the solve brackets broke a little bit. Yeah, gives you the exact same spots there. Oh, you know you're good, Taya. Don't worry. I can just close it. Yeah, so you get the exact same result either way, just making sure you want to do the in-between. So when you give your answer, you'd say something like, well, you could say t is an element of 4 to 20, or you could convert that back to 24-hour time or AM PM time. Either way, just remember that if you do convert back to AM PM, that your time values now need to be shifted 4 to the right, because t is the number of hours after 4 AM. Oh wait, no, sorry, to the left. Yeah, because this is all hours. Yeah, t is defined as hours after 4 AM. So if you have 4 hours after 4 AM, you're at 8 AM. Okay, no, how to write the first time. So in other words, maybe just stick with the t values unless they specify otherwise. Cool. Any questions there? Okay, let's see. Do they have any other interesting questions? Functions given to us, sketch graph, what times, yeah. What topic is chapter 14 of the 1 and 2 textbook? This is all circular function stuff. So yeah, this is chapter 14 of 1 and 2. Okay. Ferry operates between there, 50 minutes, only runs between, only able to enter. What's the earliest time? Oh, okay. That's kind of cute. Okay. So we got a ferry. It takes 50 minutes for it to get from its starting location to the second location. It only runs between 8 AM and 8 PM. And it can only enter the harbour so long as this function is at least 2 meters, so 2 meters or above. The question it's asking is, what's the earliest time the ferry should leave its starting location so that when it arrives, it can actually immediately enter the harbour? The earliest possible time that it can do that. That's a bit cheeky, because you've got to now take into consideration this offset, not just when is this above 2 meters, but you also need to then offset that by how long it took you to get there in the first place. Pretty cool question. Let me clear out the workspace on the CAS. We'll get some definitions going. Okay, function is equal to 3 plus 1.8 cos pi on 6x. Okay. So one of the key things we need here is to make sure that it can enter the harbour. It can only enter the harbour if the depth is at least 2 meters. So let's figure out bare minimum, when is it 2 meters? Make the function equal to 2, comma x. Do we have a domain? Yeah, I guess just 0 to 24. Shocking. Okay, we're not going to get exact values, that's fine. Well, we are, but not nice readable ones. So that means we've got a t equals 2, a t equals 9, that sort of thing. Okay, so we need to be there at that specific time. And let's just assume that it can enter the harbour instantaneously. There's no duration of time that it takes to enter the harbour. It's a light speed. Well, I guess faster than light speed actually if it's instantaneous. But let's just assume there's no propagation time there. It just needs to arrive exactly on that time. That means if it takes 50 minutes to get there, then we need to effectively subtract 50 minutes. Yeah, subtract 50 minutes from these t values. The other aspect here is not all of these t values are valid. Right? The ferry only runs between 8 AM and 8 PM. And so that means if some of our t values fall out of that range, which they will, we can't use those. Like for instance, this t equals 2 here. T is a time of hours after 3 AM. Just tried my working on the CAS, says false. Did you do the same thing? So did you make it equal to 2 or did you well actually 3 plus 1.8. What function did you define? Did you do the first line on the CAS? Yeah. Oh, I did 3 there's a multiplication there. Oh, thank God. Thank God you made me show it. Okay, that's a lot better. Okay, that's what it should be. Uh-oh. Surprised it still worked. I guess it should, because it was multiplied by a relatively large number. Okay, so maybe these won't be so bad after all then. So if we had t being the time in hours after 3 AM, then when you have 4-ish, then that's going to be 4, 5, 6, 7. So 7 AM. A little after 7 AM, which is earlier than 8 AM. So still that first answer is not going to be valid here. Which means the next possible one is going to be the 7.87, so 7 hours after. So we're looking at roughly 10 AM, a little bit, in fact, closer to 11 than anything, but yeah. So, given that being the case, we'll do that one that we're subtracting 50 minutes from. The question then becomes, how do I subtract 50 minutes from that answer? I'll get the exact one up as well, but we're trying to subtract 50 minutes from that answer. How do we actually do that? Still getting false. Are you in degrees or radians? Maybe that's the reason. Although it shouldn't be, because that's only angle related. Yeah, nah, screw that. What could it be? What could it be? How hard is it for you to send a screenshot to me of your calculator? Yeah, I'll debug that once that comes through. Anyway, for everyone else, how can we subtract 50 minutes from this time? Pay attention to the units, right? These x values are time, yes, but they're a specific kind of time. They're hours. So we have 7.87 hours, we're trying to subtract 50 minutes from that. How might we do it? So degree mode really made a difference, did it? I don't see why it would though, because it's still just height values. Oh right,
Yeah,
0 to
that's-
24.
Yeah, I think that's the reason why.
Yeah, the domain was the reason. Yeah, okay. Yeah. Okay, gotcha.
Yeah, I always forget to change it back.
Yeah, I was like, surely this is the one time where it doesn't matter, but no, domain. Yeah, oh well. And you guys have the easiest too to convert between degrees and radians. Maybe that's why actually, because it's so easy to convert between the two, it's easy to leave it on one or the other. I'm always like, no, I've got to have a default radians, otherwise it's a pain in the ass to put it degrees. Anyway, this isn't a time in hours, so 0.87 doesn't mean 87 minutes, it means 0.87 of an hour. So when it comes to subtracting 50 minutes, you're not trying to subtract 0.5, because that would be half an hour, right? That'd be 0.5 of an hour. So you want to make sure that you are subtracting 50 over 60, because you're subtracting the fraction of it such that it would become in terms of hours. And so yeah, that's roughly what we'd expect, because 50 minutes out of 60 should be most of an hour, more or less, getting us to a time value of 7.04, which we can then, no, we can leave it like this actually. We can get, this is our 24-hour time, which we can use. If you want to then say to the nearest, it doesn't say like nearest anything, so you can just convert this to hours and minutes, for instance. So 0.0417 times 60, you can say 7 hours, 2.5 minutes. So that will be 7:02 AM. Cool. So there's a few different things to keep track of there. We had the simple version of it, which was just, hey, when is the tide of the water going to be good enough? The other question was, the other part of it was, it takes 50 minutes of propagation time to actually get to that spot. So it's like, okay, cool. Now we got to backtrack 50 minutes, but not just backtrack 50 minutes from any spot, from a spot where the ferry actually runs. Okay, let's see how much of this we can talk about in the remaining couple of minutes we have. The time to go from there to there is also 50 minutes. Are those not the... Okay, it's just the other way around. Minimum time the ferry takes at the island is 5 minutes. Minimum time at the main beach is also... Time to go from there to there is also 50 minutes. The minimum time the ferry takes at that place is 5 minutes. So what, just sitting around for 5 minutes there, sitting around for 5 minutes here. What's the latest time the ferry can leave to complete a round trip in 105 minutes? It's the same sort of idea as what we were looking at before. Right, we don't have enough time to go through all the intricacies of that one right now, but it's the same sort of idea. Taking note of how long it takes you to get to a certain spot. We don't have to worry about this bit anymore, 8 AM, 8 PM, because we're still just doing a round trip at any point through there. You will have to care about it in part double I though, how many complete round trips. That one's just going to be dividing through 105 into all of this, while also considering that you start at... What time did we say we started at? 7 hours after 3 AM, so 10 AM. So considering that we started 10 AM-ish, then add a bunch of 105 minutes, and then that would give you the number of trips you could make. A number of round trips you could make. So these would be really good questions to go through in your own time, in your own practice rather, and see if you guys can replicate same answers. or better answers if you can. All right, happy to stick around for a bit for any further clarifications. Otherwise, thank you for coming.
Thank you.
Thanks.
Thank you.
Thanks. Have a
No
good
worries.
day.
Cheers.
Hey Chris, I have my integration sack on Wednesday.
Yep.
Um,
Feeling good?
I don't really know. To be honest.
Yeah. Okay. Well, what are you doing to prepare for it?
Well, remember that like worksheet from our school that we got? Just been honestly, I haven't really bothered with learning content. Just doing questions and getting AI to help me.
Oh, sure. Yeah. I mean, you're getting it right when you're doing the questions.
Yeah, I guess I'm just trying to like not memorize, just like familiarize with like the question types. Because
Yeah.
I feel like it gets really easy once you just like just translating
Yeah.
the words into the math.
Yeah, absolutely it does. But like, so you are getting them more right than you are wrong.
Yeah, I guess always the hardest part is just like the first step, honestly, and then like once I see like one line of working out, and then I'm like, okay, wait, no, I know the rest of it.
Yes. Okay. Just starting on those. Yeah. Is that yeah? And you'll are you starting to see patterns of the types of questions that are getting asked?
Yeah, yeah.
Cool.
Like I can use like for different types of questions, I can use the same.
Yes. Okay. That's what I'm heading on to. So it's not like
Parts of it.
every new question is feeling like that. You're starting to see there's some parallels of like, oh, okay,
Yeah.
I've seen something quite similar to this. No, it's not high tides and low tides, but it is daytime and nighttime or whatever. It's the same.
Yeah, because without Saks, like they do like a huge like kind of like giant case study.
Yeah, there
Poses
was
the
the
code.
data center thing or whatever the hell it was, cooling. I
Yeah,
think we had a
that
look at.
was pretty insane.
Yeah, no, it looked sick, but like
Yeah.
as we were going through the questions, what you might have quickly seen is that they're all basically textbook questions until like near the end of it. It was just like,
Yeah.
hey, what's the temperature at this time? It was more the subscript, I think, that was the weirdest part of the starting bit of that.
That really tripped me off.
Yeah, and we actually saw an example of that, maybe not here, but when we did the integration chapter review, there was a subscript N there, I think, wasn't there? I think it made an appearance sometime recently as well.
Yeah. Do
So,
you have the work solutions for the extended response 3-4 chapter 12? Oh no, sorry, chapter 11.
kind of. They're in the OneNote that I have.
Okay, that's fine.
It's a bit hard to extract those. I had a look at it and I was like,
no
it's
worries.
such a massive document that maybe I should make a new page every time I do one of these things, and that way at least I can export that and have that as a little rough working solution so that
Wait,
can-
have we done every question from the extended response yet?
not all of them, but we've done a pretty damn good amount of them.
I think are we continuing that tomorrow?
Tomorrow we're actually going to look at some. Well, actually, hang on. Your sack's on Wednesday. Yeah, we should probably do one more. Because I was going to say, because I know Nihal's looking at the probability stuff now. Your
Oh yeah,
sack,
like as
your
soon
sack is so soon.
as soon as Wednesday's done, like I
Yeah.
think we're going straight to prob.
Yeah. Okay. No, we're definitely gonna keep going on that then. I'll remind myself to not do probability because your sack is right around the corner. And
Yeah, it's
if
just
you do have anything specific to like send for that, by all means go for it because
Yeah.
it's the last time to do it.
Thanks, Chris.
Okay, let me just set that reminder. Yeah, actually, let me also have a look and see how much of it's left, because we might need you to submit stuff. Let's have a look. Oh no, we even got short answer stuff as well, which is good to have a look at. Oh no, we're not even close to finishing it. Yeah, we got.
Yeah, I think it would
so-
be good to kind of just like, I how to say, like kind of like just speed run question, just so I get like the exposure, and then I can figure it out if there's any gaps
Yeah.
afterwards.
Oh, did I skip? Oh no, actually no, we didn't. We didn't skip these. Yeah, actually maybe not. It's just like
I think
12
we
and
did.
13.
Yeah, I think it's 12 and 13. We have.
Yeah, okay. No, we should be able to do that whole thing.
Oh, easy.
Did I see a sec somewhere? Hang on. There we go. Sec squared. Nice. Anyway, cool. We'll have a look at this tomorrow.
Thanks, Chris. Have a good night.
Take care.
See you.